My presentation today will talk about infrastructure DeepQ co-developed with National Taiwan University and the Stanford University to safeguarding user data privacy. I would like to emphasize two particular elements. First element is transparency, and the second is provability. There have been some efforts trying to safeguarding user privacy. One is using data certificates. The other is using append-only logs. These two efforts, however, cannot support transparency nor provability, as I will discuss further in details. So let me start by defining some terms and explaining key privacy regulations. And there are three privacy regulations, including GDPR, developed by EU, CCPA, California Consumer Privacy Act, was passed last year and put into practice this year. Although CCPA started from California, but most people consider this could be quickly adopted by other states in the United States. And the third popular regulation is for the medical domain, and it's HIPAA. And data subject is defined as any person whose data is being collected, held, or processed. And the personal information is defined by CCPA or GDPR as information which can identify a person either directly or indirectly. So indirectly, for example, if I have a person's address and the gender, maybe I'm able to zoom in into just one individual. So although these three regulations, they have some minor differences, but their spirit are pretty much similar. And there are some common Bill of Rights. Let me summarize here quickly. So rights to consent data to be collected, and right to be informed when the data is being processed or shared, right to access one's own data, and right to erase or to be forgotten, and the right to data portability, for instance, moving my medical record from one hospital to another, and the right to rectification, making changes to my data records. A digital data privacy contract is established between a data custodian and a data subject, which covers two elements. The first element is the consent must be explicitly established or given by the data subject to the custodian. And all the fields must be opt-out, and the no box can be pre-checked. And each contract should clearly written to cover what data to be collected, how data will be used, what the user will receive as a change, and will the data be shared? If so, with whom? And there could be other customized fields as well. Once a contract has been established, the data custodian can start to access users' data based on the contractual agreement. For example, transfer data or access the data. However, the data subject can revoke the contract anytime, and the data custodian must grant such revocation. The important thing here is to be able to have agreement about the order of events. Suppose person X requested company Y to erase his prior consent, and company Y say, I never received your request, and continues to access his data, then this must be resolved in the court. So thereby, we must have a ledger system which can provide consistent views to all the transactions happen under a contractual agreement. Now that we have understood the compliance requirements. Next, we discuss the implementation requirements, and there are three. The first requirement is that our ledger system must keep indelible records for all the data transactions associated with the contractual agreement. And these transactions including contract agreement, contract revocation, and contract modification or any data assets associated with the contract. The second requirement is all transactions must exhibit the same order or consistency. The third implementation requirement is we cannot store user private data in the public on the ledgers for public consumption. We must instead storing either natural language of the contract or the code of the contract on the public ledger. The system also must ensure good performance, including high throughput, low latency at low cost. Before I present our multi-layer ledger architecture, let's visit Eric Brewer's CAP theorem. The theorem states that only 2 out of the 3 properties, C, consistency, A, availability, and P, partition tolerance, can coexist. Most distributed systems would like to ensure partition tolerance because the failures on other people's system should not affect the operations on my cell phone or laptops. Indeed, people go for CP or AP. A very well-known distributed system is Bitcoin. Bitcoin chooses to fulfill A and P. And P, for sure, they want the system to be continuously running despite some systems may be shut down. And the availability is very important to support their customers. And the shortcomings of Bitcoin, including the high cost, high maintenance cost, and also lacking scalability. And because of the proof of work protocol could involve in millions of simultaneous voters. So latency is very long, up to 1 hour. And during 1 hour, many consistency issues may occur. And another popular system is CA system. CA system only ensures CNA. Most of the airline reservation systems and banking systems are in this category. So when there is a computer shuts down in a company or in a bank, they just shut down the entire system. And they like to ensure high and strong consistency and also high availability when the system is up. But CA system, although enjoys high throughput and a low latency, but it's not really decentralized. And so it's not transparent to support our requirement of public auditing. So we like to have CAP, all 3 properties, to be satisfied at the same time. So we design a multi-layer ledger, and the top layer supports AP, the second layer supports CA, and the third layer supports our digital contract. So our system, the name is Soteria. The details we will talk about in the final session of today. And let's look at the first layer, just utilizing a public chain like Ethereum. And although the Ethereum throughput could be low, let's look at the second layer. We use a Byzantine protocol, which can support much higher throughput. Let's say we can support 1,000 throughput per second. And we only hash the root of a Merkle tree onto the main chain every 1,000 transactions, or every 1 block get filled out in the side chains. So therefore, even let's say the main chain throughput is only 10 per second, because we only upload the root signature every 1,000 transactions. So this in effect increases the throughput by 1,000 folds. And at the same time, we can replicate sidechains. If we want to support even more, even higher throughput, we can have 2 or 3. We replicate our sidechains. As long as the latency can be ensured to be low, the performance can be quite scalable. And finally, Layer 3 has our digital contract. It basically the ability is to convert natural language contract to executable code. And I will talk about the details in the afternoon session. So this picture summarizes our infrastructure for safeguarding privacy. On the left-hand side, we have this user right management system. A data subject and the data custodian can negotiate contract on this system through the user interface. Once a contract has been decided, then the contract can be returned onto a side chain. And the audit trail service here basically caching information on the blockchain in this local cache. So a data subject can just look into all the history quickly. When the person has to go to court to validate consistency or sequence of events, then the court can use the pointer cache on this audit trail service to find the real records on the blockchain. And again, in the two-layer blockchains, sidechains stores the transactions on contracts, and the main chain stores the root of a Merkle tree hashed for about maybe thousands of transactions to improve throughput. Our company, DeepQ, has successfully deployed Soteria at the Taiwan hospital to track user symptoms, drug effectiveness, and the interdrug interactions. Recently, we started to discuss with Taiwan CDC to try to develop a system to track the effectiveness of COVID-19 vaccines. The information to be tracked, including vaccine providers, patients' effectiveness, side effects, and their interactions with the parent's current condition. And moreover, of course, we need to track the antibody level generated by the vaccine and the duration of effectiveness. And thereby, we can decide when to take a booster shot. There are many entities they want to participate in this real-life human test, including US CDC, US pharmaceutical companies, Taiwan CDC, and a large number of research labs. To share information with so many entities, we have to have a scalable system to safeguarding user privacy. And I consider Soteria to be a good fit. To summarize my presentation today, I started presenting privacy regulations, including GDPR, CCPA, HIPAA, and the summarized key Bill of Rights. Then I discussed compliance requirements and converting them to implementation requirements. To fulfill implementation requirements, we developed a multi-layer blockchain architecture. Its base layer supports decentralized access for transparency and the public auditing. And its sidechains can be replicated to support high throughput and low latency. At the same time, ensures consistency. In the final session of today, I will elaborate the nature language digital contract and the executable code, how they can convert to each other for efficient auditing and also effective code generation. I finally like to acknowledge my collaborators, including Professor David Majerus and Professor Monica Lam at Stanford University, and Professor Shiwei Liao at National Taiwan University helped us to evaluate a large number of consensus protocols, and thereby our sidechain can select a high performance protocol to improve performance. Thank you so much for your attention.